Decoding the Enigma of Earth's Deepest Oceans, a Nexian documentary. What if more of our planet is unexplored than the surface of the moon? Beneath crushing pressure and eternal night lies a world of mountain ranges, canyons deeper than any on land, steaming chimneys of life, and ecosystems that rewrite the definition of habitability. This is not science fiction. It is the ocean's abyssal planet's final frontier. Tonight, Nexian takes you down to the places light never touches, to decode the enigma of Earth's deepest oceans. Chapter 1: The Vast Dark. Why the deep matters. The blue beyond the shoreline gives the impression of openness and calm. But dive deeper in your imagination, and the map flattens into a daunting fact. More than 80% of Earth's oceans remain unmapped at high resolution. The deep ocean covers most of the planet's habitable volume. It regulates climate, holds biodiversity we barely understand, and stores chemicals that could alter life on the surface. Why should terrestrial viewers care? The deep controls the carbon cycle, the slow exchange of carbon between the atmosphere and the seafloor. It is a giant engine that helps stabilize climate on timescales. Human civilization depends on it. It hides mineral wealth and energy resources. It is also a place where life exists in forms and sizes that challenge our assumptions. The deep ocean matters because it anchors planetary systems upon which every city, farm, and economy depends. Chapter 2: Thresholds of Pressure and Light. To understand the abyss, we must understand extremes. Light from the sun penetrates only a few hundred meters. Beyond that twilight, organisms endure quiet, cold, dark. Pressure increases by 1 atmosphere every 10 meters. At the deepest trenches, pressure exceeds 1,000 atmospheres, the weight of a mountain pressing on a single surface. Yet life persists. Proteins, membranes, and the biochemistry of deep-sea life have adapted to these pressures. Many deep creatures are fragile when brought to the surface, their tissues collapsing without pressure. The way evolution has solved physics in the deep is an invitation to redefine biological possibility. This threshold of pressure and light also sets practical limits. Human divers cannot go beyond certain depths. Even our best submarines require special holes. In remotely operated vehicles, ROVs are vital tools. The sea is not merely cold and dark. It is a laboratory of extremes that tests technology and human curiosity. Chapter 3: Mapping the Unseen. From lead lines to multi-beam sonar. For centuries, sailors probed the ocean with lead lines, lengths of weighted rope, to estimate depth. The map was coarse and often wrong. The 20th century introduced eco-sounding, a ping into the deep and a countdown to its return. That technology improved mapping, but the modern revolution arrived with multi-beam sonar and satellite altimetry. Scientists can now paint seafloor topography with astonishing detail, revealing underwater mountain ranges, scarps, and canyons that dwarf anything on land. Yet even with these tools, large swaths remain low resolution. Mapping the deep is slow and expensive. Each hour of ship time costs thousands of dollars, and a single mapping expedition covers a small fraction of the abyss. That is why new initiatives, international mapping efforts matter. They aim to create higher resolution maps that will guide science, conservation, and industry. The map is the first step toward understanding and stewardship. Chapter 4: The Trenches. Earth's Deepest Scarps. The deepest places on Earth are trenches, long, narrow depressions where tectonic plates collide and one is forced beneath another. The Mariana Trench in the Western Pacific is the most famous, with its Challenger Deep plunging more than 10,900 meters. These trenches are not lifeless abysses. Cameras and samples taken from the Mariana and other trenches have revealed scavengers, amphipods and microbes adapted to extreme pressures. Trenches are also geologic time capsules. Sediments hold records of ancient climate, dust from faraway deserts, and the debris of long-ago surface events. For scientists, trenches are both a window into Earth's deep processes and a living biome with surprising diversity. Chapter 5: Hydrothermal Vents. Life without sunlight. Perhaps the most revolutionary discovery of the ocean. Science came in 1977 with the discovery of hydrothermal vents. On mid-ocean ridges, seawater percolates into fractured rock, heats up, and erupts as scalding, mineral-rich plumes. Around these chimneys, life flourishes. Giant tube worms, dense mats of bacteria, clams, and shrimps cluster like oases in a desert. These communities rely not on photosynthesis, but on chemosynthesis microbes that convert chemical energy from vent fluids into biological energy. Hydrothermal vents rewrote the textbook. Life does not require sunlight. They also hinted that life might have arisen in similar conditions on the early Earth, and raised the tantalizing possibility that analogous ecosystems could exist on other ocean-bearing worlds, such as Jupiter's moon, Europa, or Saturn's Enceladus. Chapter 6. The Deep Biosphere. Life in the Sediment. Beyond vents and trenches, the seafloor itself hosts a hidden biosphere. Microbial communities live within sediments and oceanic crust, kilometers beneath the seafloor. These organisms metabolize slowly over geological timescales, surviving on trace chemical fluxes. Estimates suggest the deep biosphere contains billions of tons of microbial carbon significant relative to surface ecosystems. Studying these microbes is both technically challenging and philosophically broadening. Their metabolisms are slow, their generations measured in years, and their interactions stranger than any classroom microbe. Yet they play a role in biogeochemical cycles that ultimately affect greenhouse gases and ocean chemistry. Chapter 7. Strange and Bioluminescent Life. The deep is famous for creatures that glow. Bioluminescence is common, used for communication, camouflage, and predation, from tiny comb jellies to looming squid. The creative repertoire of the deep includes lures, glowing tails, and sudden light shows. Many deep predators use bioluminescent lures to attract prey, while others flash to confuse attackers. The morphology of deep creatures can be astonishing. The goblin shark's protruding jaw, the giant isopod's armored carapace, the anglerfish with its dangling lure. These adaptations are evolutionary responses to scarcity-efficient prey detection, energy conservation, and opportunism. To the surface viewer, the deep's life appears alien. To evolution, it is simply practical. Chapter 8. Acoustics and the Ocean's Soundscape. Sound travels further in water than light. The deep ocean is not silent. Whale songs, tectonic rumbles, and the crackle of icebergs produce a layered acoustic ecology. In recent decades, scientists have cataloged unexplained underwater sounds, complex, low-frequency noises that have puzzled researchers and captured popular imagination. The most famous of these was the enigmatic bloop, recorded in the 1990s. A powerful low-frequency sound, far from known sources. Later analysis suggested ice-related origins, but pockets of mysteries remain. Acoustic monitoring is a powerful tool. It can track migrations, detect seismic activity, and warn of underwater events. It also reveals human impact. Shipping noise disrupts whales. Sonar disturbs marine mammals, and deep-sea drilling adds new layers of sound. Understanding the ocean's soundscape is vital for conservation and for decoding the signals of a changing planet. Chapter 9. Technology of the Deep. ROVs, AUVs, and manned submersibles. Human presence at extreme depth is limited, but our machines are not. Remotely operated vehicles, ROVs, let operators explore and sample the seafloor with manipulators and cameras. Autonomous underwater vehicles, AUVs, execute pre-planned missions, mapping terrain and collecting data. Manned submersibles, like those that have descended to Challenger Deep, allow direct human observation, though their missions are costly and logistically complex. Recent advances include improved battery technologies, materials that withstand pressure, and imaging systems that can reconstruct 3D seafloor maps. Miniaturized sensors now measure chemical fluxes in situ. The toolbox expands each year, giving scientists the means to explore deeper, longer, and more safely. Chapter 10. Resources, Risks, and Ethics. Deep sea mining. Beneath the seafloor lie nodules rich in manganese, cobalt, nickel metals, essential for batteries and electronics. Companies and nations eye the deep as a resource frontier, but extraction carries unknown ecological costs. Disturbing sediments can smother slow-growing benthic communities. Plumes of suspended particulates can spread far, and loss of unknown species may be permanent. The legal and ethical framework for deep-sea mining is still evolving. International bodies wrestle with the balance between resource, demand, and conservation. At stake is whether humanity preserves the abyss as a global commons or prizes short-term extraction over long-term planetary health. Chapter 11. Climate signals buried in the deep. The seafloor records climate history. Layers of sediment store evidence of ocean temperature, nutrient fluxes, and even major events like landslides that trigger tsunamis. Ice-rafted debris tells of glacial cycles, while microfossils mark past productivity. Deep cores can paint a multi-millennial record of Earth's climate variations. Modern climate change is also buffered by the deep ocean. Heat absorbed at the surface cascades to depth, and carbon dissolved into the ocean enters long-term storage. The deep is not immune to warming and acidification. Changes in circulation, oxygen levels, and acidification will change ecosystems in unpredictable ways, with potential knock-on effects for fisheries and carbon feedbacks. Chapter 12. Human ghosts, shipwrecks, and artifacts. The abyss is not only natural, human history has sunk into it. Shipwrecks rest at depth as time capsules, cargo, records, even human remains preserved in cold, dark conditions for centuries. Some wrecks offer archaeological treasure and insight. Others pose hazards, leaking fuels or chemicals that could be environmental risks. Exploring these wrecks requires care and respect. They are archaeological sites and memorials. Technology allows us to document them better than ever before, but it also raises questions about salvage rights, cultural heritage, and the ethics of disturbance. Chapter 13. The unknown signals, unexplained phenomena. Despite decades of exploration, the deep still surprises. Unexplained methane seeps, mysterious microbe blooms, and sudden changes in seafloor chemistry challenge current models. Occasionally, researchers catch footage of creatures previously unknown to science. Each new discovery reframes the questions we thought answered. The right response to the unknown is scientific humility. The deep forces us to design flexible frameworks of investigation and stewardship, capable of adapting as new realities unfold. Chapter 14. Guardianship and global cooperation. No single nation can steward the deep alone. Oceans cross borders and currents ignore human lines on a map. Scientific collaboration, data sharing, and international law are essential. Efforts like high-resolution mapping initiatives, marine protected area proposals, and transnational research cruises are steps toward cooperative stewardship. Public engagement matters too. The deep feels remote, but its health touches everyone. Education, documentaries like this one, and policy advocacy can build the constituency needed to protect the abyss for future generations. Chapter 15. The future. Technology, discovery, and responsibility. 42 minutes and 0 seconds to 45 minutes and 0 seconds. Looking forward, the tools of exploration will only improve. Better sensors, swarms of small AUVs working together, and more robust long-duration platforms will broaden our reach. Synthetic biology may offer remediation tools, and open-source mapping could democratize discovery. But with power comes responsibility. The choices we make now about mining, emissions, and conservation will shape the deep for centuries. Science will continue to decode the enigma, but whether we act as guardians or exploiters is a human decision. Closing reflection. Nexium. The deepest oceans are no longer a fringe curiosity. They are central to climate, biodiversity, culture, and resource security. To explore is to learn. To learn is to choose. We can map this hidden world and treat it as a shared legacy, or we can plunder and lose it. If the mystery of the deep moved you, subscribe to Nixie. Share this film with someone who believes the ocean deserves more of our attention. And tell us in the comments what surprised you most about the deep hydrothermal life, the pressure-adapted creatures, or the risk of deep-sea mining. The most thoughtful replies will be featured in our next episode. This was Decoding the Enigma of Earth's Deepest Oceans, a Nexian documentary.